All right, section 4, energy of simple harmonic oscillators. So we have kinetic and potential energy of a spring mass. Energy of harmonic motion is a transfer between kinetic and potential energy. So all we're really saying is that if our equilibrium is here, we're going to call this x equals 0, where that would be the equilibrium position. Then here at x equals the maximum displacement, the amplitude, well, this is going to be our most potential energy, only potential energy, and here we would have all kinetic energy. If we were to, this would be all potential, all kinetic, and anywhere in between here, K plus U would have to equal E total. So this would be equal to E total here, this would be equal to E total here, and in between you'd have to add them together. So any energy should still be conserved, which just basically means when we're adding these together, we should get a total at any time of the two added together. So here is a great way to show it. We've got three superimposed graphs. We have the kinetic energy graph in red. We have the potential energy graph in dark blue, and the total is in teal. So at any point along this line, if I add these together, I should get the one on top. So extremes would be all kinetic, no potential. That's going to be at the top there. We have the half and half. We're going to add them together, we get a whole. We have all potential, no kinetic, we're going to get that point at the top. All right, and this should be a straight line. If this is not a straight line, that indicates that our energy was not conserved. Graphing energy versus position. Well, here, instead of it being energy versus the time it takes, when we have energy versus position, we're still going to see that at the equilibrium position, we're going to have total kinetic energy. And at the amplitude, we're going to have all potential. But at any other point throughout, we should still get the total at the top here. All right, as promised, here's an equation for the spring mass system. The total energy is 1/2 K A squared, where A is the amplitude of how far it's been pulled back. This does matter. This does not matter when we're talking about the period of the pendulum, but the amplitude does matter when we're talking about energy. So there you go for the spring mass, and we're going to go ahead and use that in the examples. And then here we have kinetic and potential energy for a pendulum. Well, at the top here it's going to be all U, the bottom here it's going to be all K, and this says release from height, how fast we'll go at the bottom. Well, the total has to be equal to a constant, so the change in potential energy should equal the change, plus the change in kinetic energy will equal to 0. So all the potential energy here will become kinetic energy at the bottom, so U equals K, and wants to know how fast at the bottom, so we're going to plug in our equations. MGH equals 1/2 mv squared. Our m's cancel. We get v is equal to the square root of 2gh. All right, I'm going to stop this video and make another one of the examples just to keep these short.